Hello, I am Ji-young Choi, a second-year master's student in the Department of Chemical Engineering at Sungkyunkwan University under the guidance of Professor Junhyuk Lee. I am conducting research on OLED material synthesis, and today I would like to present on the development of high-efficiency and long-lifetime platinum complex for OLED blue phosphorescent material. The table of contents is as follows. Firstly, I will give a brief introduction to OLEDs. OLEDs, or organic light-emitting diodes, are electronic devices that emit light through the use of organic materials. They are made up of layers of organic molecules stacked on top of each other on a substrate, which is typically made of glass or plastic. The layers in an OLED include an anode, a hole injection layer, a hole transport layer, an emission layer, an electron transport layer, and an electron injection layer. When a voltage is applied across the device, electrons are injected into the electron transport layer from the cathode, while holes are injected into the hole transport layer from the anode. The holes and electrons then move toward each other and meet in the emission layer, where they combine to form excitons. These excitons release energy in the form of light as they decay back to their ground state. The emission layer is typically made up of a thin film of organic molecules that have been designed to emit light when excited. The color of the emitted light can be tuned by choosing different organic molecules with different emission wavelengths. The emission mechanism can be divided into three categories. The first is fluorescent emission. Fluorescence emission is a mechanism in which light is emitted by singlet excitons formed in the emission layer of an OLED device. Unlike phosphorescent emission, it does not require the use of heavy metals such as iridium or platinum. Fluorescence emission has the advantage of shorter lifetimes, typically ranging from 10 to 100 nanoseconds, but it can only utilize the 25% of excitons formed as singlet excitons in the emissive layer, leading to a maximum efficiency of 25%. The second mechanism of emission in OLED is phosphorescence, which uses triplet excitons instead of singlet excitons to emit light. This process requires the use of heavy metals such as iridium or platinum to induce what is known as the heavy atom effect. In contrast to fluorescence, where only singlet excitons can emit light, phosphorescence can use both singlet and triplet exciton to emit light. This is because the heavy atom effect facilitates the conversion of singlet excitons to triplet excitons through a process called intersystem crossing. This conversion process allows up to 75% of triplet excitons formed in the EML to participate in emission, and up to 25% of singlet excitons can also contribute to emission by undergoing intersystem crossing. This leads to a maximum quantum efficiency of 100%. However, the disadvantage of phosphorescence is that it has a longer phosphorescence lifetime in the microsecond range, which can limit its application in certain areas. Lastly, TADF, or thermally activated delayed fluorescence, is a mechanism that can convert triplet excitons into singlet states through a process called reverse intersystem crossing. This is possible when the energy gap between the lowest singlet excited state and the lowest triplet excited state is small, typically less than 1.4 electron volt. In TADF materials, the T1 state is located close in energy to the S1 state, allowing for efficient RISC to occur and leading to fluorescence emission. Next, I will present my research on high efficiency and long lifetime PT complex for blue pitch OLED. As previously mentioned, the phosphorescent mechanism of pitch OLED requires rare metals such as iridium or platinum to induce a heavy atom effect. Among them, PT complex PD02, a material published in Nature Photonics in 2022, is a complex that has advantages such as high efficiency, long lifetime, low driving voltage, and low turn-on voltage. My research goal is to create a new PT complex with improved lifetime and efficiency over this material by replacing the ditertiary butyl phenyl group of the reference material with another substituent. A new PT complex was designed by attaching bulky groups A and B that induce steric hindrance, resulting in a narrower FWHM and longer lifetime. Firstly, the DFT calculation results show that the energy gap and triplet energy are similar to that of the reference material. However, the dihedral angle of the upper part of phenylimidazole was larger than that of PD02, indicating greater steric hindrance. The photophysical properties were evaluated for PTA material, as the PTB material is still in the process of synthesis. The HOMO and LUMO level measured through CV showed almost the same value as the reference material. The FWHM of PTA is narrower by about 5 nanometers, indicating the effect of strong steric hindrance. The electroluminescence properties of the PTA material showed a slightly reduced FWHM compared to the reference material. Although the efficiency and turn-on voltage of the device are lower than the reference material, considering the lifetime and FWHM, the PTA material shows comparable excellent device evaluation. With the promising results of PTA, I plan to introduce and synthesize new PT complex with new bulky ligands and develop a new long lifetime, high efficiency PT complex through device evaluation. Our ultimate goal is to develop a PT complex that is suitable for commercialization. Thank you for listening.